pull request that I have going on to onto the objective functions that I just wanted you to have a look at. I will share my screen here.
You guys can hear me okay?
Yeah, that's great.
So Dom, it's just this objective function multipliers pull request, number 585.
Okay.
So all I've done here is instead of the multiplier being accessed from the underscore namespace, now they're just in the top level namespace. Because I thought that they are something that you probably actually want to easily access.
Can you give me an example?
So before,
Sorry.
Yeah, no worries. Before, like if you look at this example here, so I've got this assert 53.multipliers is np.r24. Before that would have been assert 53._multipliers.
Okay.
So in this case, like all that I've done is I've brought it up a level and then I've also put a setter in. So basically just to make sure that you give it something that's sane. So I wrote a test. I'll show you. That's kind of like a helpful thing to look at. So at the bottom here, there's a test updating multipliers. So for example, if you try and give it a string or a list of strings, it'll fail because we don't know how to multiply by that.
The third case is if you give it an array instead of a list. Is that the difference?
Oh, you should be able to give it a list or an array. Either of those are fine.
No, but what's the third case? The if.
Oh, so here there's only two. There are only two objective functions. So if you try giving it something that is length 3, that doesn't match.
Yeah.
Yeah.
That's great.
Yeah, so I'll let you like take a quick look. I didn't know if that would change any of your code, so I didn't want to merge it in without a thumbs up from you first.
Are you merging on my PR or it's a different PR?
This would go into the objective functions.
Okay.
Into the ref objective functions pull request.
Yeah, I need to. I think I'm behind you. You pushed a few commits, so yeah, do it, and I'll adjust.
Okay, sounds good. I will do that right now. Perfect. Cool. All right.
All in.
Cool. So did you guys want to go over time domain EM first, or do you want to go over the BCGS top?
It's up to you guys. Go Seogi, I would say, and let's finish with the BCGS.
Yeah, I'm pretty open. Like, do you know when is that BCGS? Is that the?
So that, let me just pull up the email. There were two options. There's one in May, which I think would be better, and then there's one in June. Okay, so Thursday, May 18th or Thursday, June 15th. So I would vote for the 18th, for May 18th.
Yeah.
Because June, you're going to be gone. Probably.
I'm okay with that.
Yeah.
That leaves us how much time? A full month. Yeah.
Yeah, which I think like that should be fine. I mean, like a lot of this stuff for background material we have, and then we do have a ton of examples. So it's just a matter of like pulling together and highlighting a few things that are most relevant to that community.
Yeah, absolutely. Who's you want to give it the talk, Lindsay?
I'm easy. We could sort of do like, how long do we have, Dom? It's like an hour, right?
Yeah, we could
Yeah.
also all stand if you don't want to have to do it all. You know, you can partition it.
Yeah, because in some ways I think it could be kind of cool to like like I'd be happy to give a bit of an overview and then have you guys talk about examples that you're working on and kind of have a bit of a mix.
Sounds good to me.
Yeah, because that sort of then it gives a chance for people to ask questions and like we can try and maybe plan for like a 45-minute length presentation and then that gives people a chance to actually ask questions and have a bit of a conversation afterwards.
Right.
Yeah.
Seogi, which you gave a talk, right, with TKC and Sarah? Was that a BCGS talk too?
Yes, that was a bit just one.
So
Did
they've
you
seen TKC already then.
But I think that this not, that BCGS talk was for a conference, BCGS conference. I don't think because it's more internal workshop, right? Like where they go to a small like conference room below the Mira's office, I guess. Is that something that we were doing, or is that a conference?
I can ask. I'll ask him when he's talking now, but I'll ask him once he's done.
I think this is the small workshop with like their monthly workshop, I guess. So it's more like internal workshop, and then I think we got the bottom.
I think so too. Yes.
Yeah.
So yeah, I like the idea. So if you're a game on like overview, and then what was his name? Thomas. It was
Yes.
he was suggesting demoing like some of the codes. I think like probably like showing a quick example that'll like if you can run on Alive, that
Yeah.
that's probably more effective for them. They're very practical guys, like
Yeah.
so I'm not like exactly sure what's so like to ignite their interest, I think we should show some examples.
Yeah.
Yeah, we could do like 2D DC, potential fields, 1D EM, I guess. Lindsay, we could do that live, right?
Yeah, we can do all of those live. I think like in a lot of ways, live demos, we have to be really careful with them because it is very easy to sort of get carried away and just show a ton of code. And because we're familiar with it, it is like easy for us to get to, but otherwise it's actually pretty intimidating.
Right.
Just to run.
Yeah, quite true. So I think like maybe if we pick like one, maybe potential fields and maybe DC, and then just show the rest and like because we can point people to like the Azure notebooks and make sure that we've got a few more examples up there, so that we'll show sort of what we have and then show a sample and people can go from there.
I think probably like a demo is one example is enough.
Yeah.
Like not too many examples. Like probably just show math and gravity that can run relatively fast. And then like other example could be just in the presentation.
Yeah.
That's a good idea.
Yeah, like probably one demo and then a couple examples.
Yeah. And what do you guys want to show for examples?
I think I would do DC and IP.
Okay.
Well, that's what like their conventional tools, and then probably what I would show what they usually do.
Yeah.
And here's an open source code that you can do it.
Mm-hmm.
That's what I would do.
Okay.
If I'm doing it.
Yeah, no, absolutely. And then Dom, you want to show like the compact norm stuff, maybe a joint version?
Yeah, I think the new mag would be interesting because that's new code that people can start experimenting with, and there's a need for it. So yeah, we just can start sketching it out.
Okay. Maybe what we can do is like get a Google Doc started and just sort of each of us put like what are the things we want to get across, and then we can sort of plan for basically like 15 minutes each. And then we can shuffle that around as needed. Like if we need more time for one of the examples or not, like we can figure that out. But yeah, if we sort of start with a bit of an outline, that can hopefully get us through.
And we want to do synthetic, right? Which is going to be easier.
Yeah.
I think so. I mean, if we have like, we can point to other field examples like Craig stuff and just sort of highlight a few of the real things that we're doing.
Right.
But yeah, I think for demos and things like that.
Yeah, we could just
that is fine.
probably use TKC example. And like use a common example at least
Yeah.
to show what you can do with that.
Yeah.
How about we build something that we can distribute? Because then it would be nice, right? The participant could always go back and just run it on their own computer.
Yeah, perfect. Yeah, I'm open-minded to whatever example, but like if you can build a common model and then show probably like 2 examples,
Yeah.
and DC and IP, that probably good.
Yeah. Do you want to do the TKC example, or have we?
I'm a bit sick of it, but I'll think how much time we want to spend on it, I guess.
I mean, do you guys have another sort of example with surfaces in mind that, like a model that we can use? We can give it some thought.
Right. Do you have a good example, Tom? Do you have a synthetic model that you can use?
I was going to build one for my paper for the Kivitz model because we already have surfaces and it's a nickel deposit, so it's different than diamonds.
Oh.
It could be a little bit more interesting, but it depends how much time how fast I can deliver it, I guess.
Well, yeah, for like, it depends upon like the purpose. Like, if you want to provide something easy and quick example, like we should make it much simpler.
No, yeah, it will be simple, yeah, for sure, yeah. I'm just thinking base metals is probably better than diamonds for the crowd because very few people do diamonds in Vancouver, so.
That is true. Right.
It's a porphyry, right? It would be perfect for IP because it's technically chargeable and.
Yeah, actually, yeah. If you have some thought, I'm it's a bit of like a distraction. I'm thinking about building a kind of porphyry model.
Okay.
Well. So, yeah, that'll be good.
Oh, but then that's great. Then if it's going to be
Game
used by other.
Spending a bit more time on that then, because like anyway, I need an example for research stuff. So that'll be great.
Okay, well, I'll show you I'll send you the section, the simplified section that the judge just made, and if the geometry looks good for you, then I'll go for it.
Oh, that sounds great to me.
Okay. Sounds good. I'll fire it to you right now.
Perfect.
So are you guys both good with then the May date? If we send that email back to Thomas?
I'm happy.
May 18th?
I'm happy, yeah.
Perfect. Cool. I'm looking forward to that.
Yeah. It's a Thursday. I think it's 4 p.m., I guess.
Yeah, I think that's what he said. 4:30 is what his email said. So we can confirm that when we follow up. Don, do you want to follow up with him? Is that all right if you take that on?
Follow up with Thomas?
With Thomas.
Yeah, I'll talk to him right after the meeting.
Perfect. He's at Mira?
Yeah, sitting right behind me.
Oh, wow. Cool.
Okay, that's an interesting section.
Yeah. I think I'm happy with that. Where is the mineralization? So that the gray unit is the mineralization, or the?
1 second, I'm just gonna send you 2 more, man. The surface and the. The mineralization would be decimated inside the dark gray.
Okay.
I see. Okay.
And the and the light gray on top is super magnetic, so that's a good target for me. And then You'll see on the section, on the plan view.
Right.
You have the plan view now?
Yep.
Got it.
Yeah, so it's seen from the top, and all those bands are actually have contrast, so we could, we could put values in them.
Right.
Oh wow.
And the like a kind of region of interest is about 2 kilometer by 2 kilometer, or is it?
Let's see.
Oh no.
No, it's way more. Yeah, that's about I think 15 kilometers square. But the mine is about like the pit is going to be about 1 kilometer wide.
Okay.
You see the white dash lines, yeah, where you're thinking, it's about 1 kilometer.
I see.
Okay.
Cool.
Yeah.
Okay. That sounds good to me.
And this is the one that you're also doing the joint mag on?
Yeah, that's right, and that's the one that they did like seismic interpretation. So we also have 2D seismics that we could just tease people into the problem,
Cool.
Wow.
And we have, yeah, exactly. If we have something nice, we could share it with our people in what the hell, I forgot, university, whatever. There's more people that are going to be interested in seeing it.
Cool.
Helsinki, is that a number? Yeah, that's one, right?
Helsinki?
Yes. Thank you.
No worries. Cool. Okay, awesome. One place we can perhaps put those for now, there's a repository that was started back when like the TKC stuff was going that we've never actually put anything in, called GeoModels. So it's SimPEG/GeoModels, and like the goal there is to have some of these models where we've got surfaces and like physical properties assigned to rock units. So we could perhaps start by putting like the surfaces and even just the maps and a few things in there, and just because right now there's nothing in this, so we can sort of start to define what it should look like in terms of actually storing models that people can then go ahead and use.
Okay, yeah. Perfect. It's the same idea, pull request there, or we can push directly?
I would maybe do a pull request for now, and that's like a thing then that we can talk about, but there's really, we can merge it in pretty quick.
Okay.
I'll post that on there. Cool.
Nice. Cool.
Up to you, Seogi, now.
Yep. Oh, okay, yeah. Right. So.
Or I can plug it in and share my screen. That's as far as this goes.
Yeah.
Or yeah, if you share your screen, we're good to go. Do anything HTML.
Yeah, so I I need some functionality for galvanic source. So Lindsay did the refactoring for both frequency and time domain code. And I think recently time domain code.
Yeah, it's pretty recent.
Yeah. So I think that's usually how it works. Lindsay changes things and then you can have a look. So here's the setup. Like this is a Maxwell's equations, and like we've got magnetic field, electric field, and current elements. So SE is an integrate current, and it includes all the volume terms. And here's Faraday's law curl of E is equal to di E di T. And then we use the Bagel-Euler to discretize that. So here's the setup. And then we have a time step starting from 0 to nt. So we have nt plus 1 steps. Well, like time step is actually nt, sorry. But like your electric field and magnetic field have nt plus 1 like times. And that's set up. And we solve E, so we can rearrange that equation in this form. So we can solve for E. So we got like E at n step, n minus 1. So n minus 1 is known, so you can move that to our right-hand side. And at the end of the day, and then here's what's important, is like we compute the derivative of, time derivative of SE. So that's a little bit different. So if you write that in like as a function of b, then there's no time derivative, but there's SEN. But like that's a little bit of difference between what either you solve E or B. Bit of detail. So I'm not sure what's the extent of today's talk, but the idea is like actually going through a little bit of details and then show the implementation. So that's sort of my goal. So I'm not sure you guys are really interested in that part, but that's what I'm doing. So, okay, cool. So you can write that in a little bit more abstract form. So A at n and un plus bn and un minus 1 is equal to right-hand side. So in a matrix form, you can write in this way. So here's like everything is sort of conceptual. Like you can make a big A bar matrix and then U bar and then RHS bar. So that's the system what we're solving. We're not going to solve this full system by A inverse of right-hand side bar, but like this is sort of conceptual thing that we built. And then and the for problem, it's like it's a for substitution, right? Because like this guy is a block matrix, but you know all of these terms, you can solve that. But after that is actually like just for substitution to solve this system. Okay, so that's how we're solving. And the main kind of implementation that I had to do is like this step when n is equal to 0. So usually if you're using inductive source, U naught is known. So what we do usually for inductive source, we compute the magnetic vector potentials and compute the B, and then B naught is now known. So that means B naught it's independent on your conductivity structures. But if your susceptibility is like variable, then still U naught is depend upon your model. So in that case, you should be careful. Like so, depends upon what your model is, and then dependency on your initial fields at 0 time. You need to be a little bit careful. So previously we assumed our initial condition is not dependent upon our model, but like if you're putting a galvanic source or grounded source, now your initial condition is a DC problem or an MMR problem. So you need to solve that initial condition by using DC code and then put that into U naught. So like now A naught is it's a Poisson equation to solve, and then your right hand side it's like +1 and -1, for instance, for DC. So you need some like a consideration on that part. And then like so that DC problem can be discretized as like this. So here I'm only focusing on EB formulation. So I'm using a nodal gradient. So nodal gradient moves nodes to edges. Okay. So this is the edgy inner product, and then this gradient transpose is basically similar to actually same to divergence.
So when you're implementing your source for that, you're not. You actually have to. Do you have to change the source between the DC and the EM problem? Is that like in one you just have the electrons?
I'll get there.
Okay.
Yes. So there's another implementation is required. Is like okay, how do you compute the right-hand side,
Okay.
right, for this case.
Yeah.
And important thing, if you go back to here, like U naught here is an electrical field, and then but we're not actually solving an electrical field for DC problem. We solve the electric potential and then take the gradient to get the electrical field. So here, like in an abstract form, A naught is number of edges by number of edges, and U naught is the number of edges. But we're not quite solving that system.
Right.
So you need to be smart. So you need to make some sort of function handle which does this. So for 4 problem is okay, but when you move on to JVAC or JTVAC, it's kind of important. You need to think about your force in like a force sensitivity and an adjoint sensitivity and as a function handle, which is a little bit tricky. Okay, so now I could move on to okay, so at the end of the day, what we're doing is like we solve this system for each time channel, but you can write that in this form as well. But we're not actually computing the full A inverse, but we're solving each time channel. So we're looping over time. Well, the question was like in reality, our signal is like it's periodic function. So but we're assuming like one period at a time. So that's not quite true. So there's a way that we could like implement in that way. So we could assume the periodic function and then solve a periodic set of periodic boundary condition. Then you could get the periodic response. So there's a way. I'm not exactly sure, but that's probably something like this. So if you pick the periodic boundary condition like this, then you may obtain that, but like not now. And so there's some practical consideration that needs to be taken care of. So now JVAC is like we need to compute the derivative of our fields at nth time channel regard to conductivity or whatever inversion model. And at the end of the day, you could get this form. So basically, it's the same way to solve the system. So we need to solve this forward problem for substitution. We could just forward substitute this block matrices to solve this sensitivity function, and then you do time stepping. So here, that's the reason why it's important. Like that is not like we're not quite solving this A naught, but like a smaller system, but we still need to solve smaller system and then sort of surject that to edgy spaces. So like there's a bit of details.
Well, you're looking at the fields rather than just the solution vector, right?
Right. Yes, and then like when we're solving the adjoint system, it's similar but not like right. So like now, not like your first solve is at here. So backward substitution actually starting from the latest time and then backward propagate to a first time, but still like you need to be some like consideration on this first time channel because of different size and different matrices. Okay. Yeah. So that's how it works, and yeah, there's a little bit of details. I'm not sure. It's like all of them needs to be taken care of here, but like that's the gist of what I had to change. And then yeah, so that's it. And I'll show a little bit of implementation wise. So important thing is remember that right how we compute the right hand side. For instance, so it's not a great figure, but the geometry is like, so you got, say for instance, this is a synthetic model, and then my wire path is goes like this, for instance. Like that's a horseshoe. So how you set that wire path is like this. So you need 4 points, to define that horseshoe, and then you pass that point so you can stack it, as source location, XYZ location. Then here's source.line current. That's how you build. And then you need to pass the waveforms. Here I'm using step off waveform. So now this line current function is smart enough to integrate over the path. So I'll show you how that looks like. Okay, so here's a line current function. And then I have a source type called galvanic. Because this function could have a multiple use. So if the point is not closed, then that's a galvanic source. But if the point is actually completely continuous and then closed, it could be an inductive source. Right. So that was a reason why. And then in that case, you don't need to compute the initial condition. Or you still need to compute the initial condition, but
you don't have to include the source.
Right, and then actually for inversion, it's not dependent upon the conductivity. So so that was the reason why I put the tag on it.
Yeah.
Because there could be multiple use.
Okay.
And then, so here.
Do you like, and this is a question because I remember we talked about this at one point, do you like galvanic or do you like grounded and inductive?
Yeah, I think I like the galvanic. I'm not sure grounded is, grounded could work, but people use sometimes grounded loop. Or maybe they may not use grounded loop, but ground loop. So there's a difference grounded and grounded and ground.
Yeah.
So as long as
there's a bit of ambiguity, because a wire source there is an inductive component, even if it is grounded.
Yeah.
But I think I'm fine with it being galvanic. It just
I'm open-minded. If people use grounded, I'm okay with that. But that's anyway. We need some distinction of the source type here for the implementation. And so I have for instance, get right-hand side, and then here's how I'm computing the right-hand side. So if you think about it's a divergence of JS at your right-hand side. So once you form a JS, then you can just simply take the gradient transpose.
Oh, so this is okay.
So
this is the right-hand side for the DC problem, not for.
Right. But if you actually think about what's happening, for instance, say you have a wire path up here, from here to here.
Yeah.
And then if you think about taking the divergence, you're going to get all the zeros along the wire path.
Yeah.
But you're going to get +1 and -1 at the ends of your line current. Right. So that actually effectively generates +1 and -1 at the source location, at the electrode location. So all the inductive part is gone by taking the divergence. So that's actually how it works. And here I need to compute the E initial, so I compute so I can get the solution DC and then take the null gradient and get the electrical field. And then here's a derivative. Yeah. Because that derivative is taken care of. So that's, I haven't implemented the magnetic field one. So if you want to compute the magnetic field on the off time, so you need to be taking care of the magnetic field. No matter what you solve E or B, you should take care of that to get the right response at that. But if you're just interested in electrical field or dB/dt, then you don't quite have to. So at this point, it's not quite working.
Okay. Would you mind writing an issue
on
that, just so we have it documented?
Right. Okay. Yeah. So at least I put errors. So if you try that, it gives you errors. Right. And at the end of the day, what we're calling is SE. Yeah. So that's how it looks like. So MEJS, it's basically, we still need a distinction of SE plus some time function. So this time function actually provides a current waveform.
Sorry,
because you call MEJS, like integration of JS as an SE.
Yeah.
So it just inside, like I'm just calling that part and then multiply waveform.eval.
Fair enough.
So that's how it's structured. It only works for EV formulation. Right. So that's the source term. And for problem, so I didn't change at all about the field. So yeah, I like how you're doing get initial fields. So this actually makes stuff working. So once you call the get initial fields, that calls the DC problem, yeah, so that actually computes the initial fields. For problem, I didn't have any problem. I had to change. I think JVAG was fine. I didn't have any problem. So the current structure actually did work well. So I didn't change anything on JVAG. And for JTVAG, I had to change. So I don't know. I think, yeah, I didn't want to break it. So I put it on like the EV formulation. So, but I had to build like, this is the probably some part I had to change, but I think I didn't change in a general problem class.
Yeah.
Handling class. But I think I did change problem E. Okay, so if you look at now there's an ADC in.
Yeah.
So I want to store the factors because like I don't want to regenerate it for every time.
Yeah.
And then for all the values. Okay, so only.
But you're still clearing it after like every model update, right?
Yes. Okay, yes. I think I probably do it in the get initial fields, I guess. Whenever I compute the initial fields, I think I do, right. Yeah, here.
Okay, cool.
So that's how I'm doing it.
Right. So anytime you're getting
right.
them,
whenever I'm updating the fields,
yeah,
I do clean. Okay. In that way, I make sure I'm not like, for one Gaussian Newton iteration, I'm not updating it.
Right.
But after like you move on different iteration, because like you only have one fields call for one Gaussian Newton iteration. Like for JVAC, JT that you've already computed, so I think current syntax structure works in that way. So it's smart enough, like they're not going to recompute the fields for like JVAC and JTVAC.
Right.
So yeah, so that case, I think this works. Okay. Yeah, so here's get ADC, for instance, and I'm not sure. Yeah, I kind of like putting here. We could think about that. And only things that I had to change was here. So so this is when t is equal to -1. Like that part is not taken care of in your code. Because like
that, yes.
Yeah, because like, well, if you think about like it's starting from 0, right?
Yeah.
But like we have a -1 step actually, which is an initial condition.
Yeah.
So I did put that t is equal to -1. Okay. So we can definitely put it in. Yeah. Right. Then we need to generalize here. Like I have an ME sigma deriv and that types of things.
Yeah.
So then like you need to be taking care of your HJ formulation. So there was like enough complexity that I didn't want to handle.
Yeah. So
that was the reason why I put it in like as a separate class.
Yeah.
Right. So yeah, that's about it. And this is where I'm taking care of like more like in an abstract way. But actual implementation, I'm solving DC problem.
Yeah.
And then computes the electrical field in the same way for sensitivity and sensitivity vectors.
Yeah.
So that's how it works.
That's awesome.
Right. So this is sort of the result. Like it's a fairly simple example. Like you put 5 time channels of yeah. So my time step is pretty small. I've only got 6 time channels, and like 1 millisecond to 6 millisecond.
Yeah.
And then I can invert it. It probably takes several hours. So which is like pretty big time compared to DC. I think for like my DC inversion, the same case, it probably take like a couple of minutes. So yeah, it's intensive doing time domain. But I think there are a lot of improvements could be made. Like for instance, we can store the factorizations.
Yeah.
That'll like boost up the log for a small problem. And this is the result. Like so, yeah, it actually works pretty well. So here I'm using H2 3D to generate synthetic data, and then inverting using SimPEG code.
That's really cool.
Yeah, so it's not inverse crime.
And those are on the same color scale, so we're actually like
Yeah, it's the same color scale.
getting into the right. Oh, that's cool.
So galvanic source is actually pretty effective
Yeah.
to find both resistor and the conductors.
That's awesome.
Yeah, so it's a simple example, but so it works. Yeah, it's basically the same example that I use in my paper, so
Yeah.
it works pretty fine. Yeah, and then there could be multiple use. I'm using the step off waveform now, but if you're using general waveform, like all the problems just should work.
Yeah.
So you could do, well, like you could do EV formulation, but you could do B and also E. In that case, like all the sensitivities and should be like it's tested, so it should just work.
That's awesome.
So only it's not like just you just need to be careful when you're using the step off, and then your data is B, then it may not work.
Okay.
So other than that, that's other things are.
That's really cool. One of the things I wanted to bring up with the waveforms too, like you can go in and add waveforms to the time domain class. So something like a V10 waveform, you don't necessarily have to give it like the raw waveform plus the interpolation function handle. You can go in and add that under the hood if that's something that would be valuable.
Right. Yeah, that's something that we could do probably using the properties. And what I was hesitant because like they're changing.
Yeah.
So they're changing relatively fast.
Yeah.
So every year is like
It's different.
they have a new system and then they have a different time gates.
Yeah.
And also different survey use a different time gates and different waveform. So I wasn't sure what's because like it's sort of dangerous then.
Yeah.
Because like people like because like I think I would, and for our code I think I would like kind of make a trade-off. Like we're not going to make it really easy.
Yeah.
But you just need to think about what
That's
the
fair.
waveform is.
Yeah.
And then what your time channel is. I don't know. Like some people may just give up at that point. I think that's fine.
Yeah.
But you just need to really like we need to force them to think about what that is.
Yeah.
And then actually, oh, okay, I need to discretize this. I need to put it in.
Yeah.
I think that's a valuable step.
Okay, that's a very fair point.
I don't know, like as what your friend like from Colorado.
Yeah.
Because like I think she didn't have any idea, I guess, like what's
What
like what she has to do.
Yeah.
She knows that's a V10 waveform.
Yeah.
But she doesn't know what like needs to put it in.
Yeah.
Then that doesn't necessarily mean like she's ready to start.
Right.
So she needs to understand what she needs to put it in.
Yeah.
Then like okay, somehow our structure should force them to. We can make it a little bit easier.
Yeah.
Like from now, because like you need to generate the interpolation function and then pass it through.
Yeah. Yeah.
We can like kind of simplify that.
Sure,
that
but
step.
actually having to provide it is a good idea.
Right.
Yeah.
Anyway, or like we can put like a little bit more parameterization to V10 waveform at different times and like change the parameters and those type of things.
Yeah.
Yeah, not too easy.
No, that's a great point. That's a great point.
So my to-do list is something like that. So for simulation, I implement the initial condition, not for MMR problems. So MMR has not been implemented, so it should be done. So JVEC, JTVEC is done, and to-dos like we need to solve B, so EV formulation, solve B, HJ formulation. So it's not working for step off function. That's probably a to-do. And I want I don't know, like if someone has a bigger example and then they are having a hard time, like probably might, you could make it a little bit faster.
Yeah.
And probably sort the factorizations. And for a for problem, we're storing the fields, but for a problem, we don't quite need to store the fields.
Yeah.
So, and especially for EM problem, it's pretty big.
Yeah.
When it's
So we
got
should have
like,
options around that.
yeah, a lot of sources, then your fields is huge. So even just running the for problem could have some problem.
Yeah.
So we may have an option to not store the fields.
Yeah. The other thing too, like even for the inverse, you don't actually need all of the fields. You need a footprint. Like there's a
right.
You only need some of them. So that would be a good thing to
Right.
think about implementing. Is basically just like that stencil that we need for the fields.
Right. You can solve as you go.
Yeah.
As well. Some practical considerations is the receiver. So now, like, receiver has some function. For instance, like people use the filters.
Yeah.
They put a low-pass filter usually for instance, DC and IP data. So in their early time, like they have a rear decay.
Yeah.
And also for airborne case, they put a filter. So they usually put low-pass filter to get a nicer late time data. But that kills the early time data, which is interesting. So I'm not sure. I'm not sure that's like we need to implement it in the inversion code, but that's some practical consideration. So time integration. So what we're getting is not a point value. So they have time gates and then integrate over the time gates in both like any types of EM survey that does it. So that sometimes needs to be taken care of it.
Yeah.
I think that's probably important for airborne case, especially when your decay is really fast.
Yeah.
So receiver, like that line integration code can be used for receiver as well. So we can build a receiver. And the source, when source is inductive, and then you have a whatever wire path, you could both actually use that line current, but we can actually use the vector potential to integrate over that path. So those are some practical codes that needs to be done to be used for actual practical cases.
Yeah.
So I think I would focus on probably these two first, which is easy.
Yeah.
I'm not sure about these two. Depends upon who you talk. People have a different opinion.
Yeah.
So that's what I'm trying. So I'll put that into an issues. So that'll be good.
Nice. That's awesome, so. Yeah, I mean, I think once you've got sort of issues documenting where things are, let's get this into EM dev, and then we can go and sort of try and generalize from there afterwards.
Yeah.
I think it's up and running, so we might as well start using it.
Right. So yeah, if we can merge this, because I have a colleague I met in Indonesia.
Yeah.
Amir Harun. So he wants to use.
Yeah.
But
That's
yeah,
awesome.
I got an email oh, it's not working because he just installed the SimPEG through the pit, I guess.
Okay, so okay, we can also start deploying pre-versions. So we can deploy beta releases and things like that. So if there are instances like that come up that you want to install a pre-version of SimPEG,
yeah.
we can do that.
Yeah, no, not in a hurry. So I can give him a different option, but if I can merge to EM dev now, I'm happy with that.
Perfect. We can make that happen. Nice work, Seogi. That's really exciting.
Oh, thanks.
Yeah, that looks like a lot of work. Congrats. And it's inverting.
Pardon me?
And it's inverting. That's good.
Oh, yeah. Well, I'm just usually impressed whenever this just conventional inversion just works.
Yeah.
Yeah, we finished the sensitivity and sensitivity vectors and for simulation. We test it, and yeah, it usually works, which is pretty impressive.
Yeah. Very cool.
Okay.
Yeah, anything else you guys want to go over today?
No, not specifically. I have a question for you, Lindsay.
Yeah.
Can problems share things? For instance, let's say you had factorization that you wanted to pass on to a joint problem, right, to the other problem. Can you do that?
We don't have that set up right now, but we should be able to. So you want to store you want to store factors between problems.
In my problem, like I have to create twice the sensitivity matrix, which is expensive to do, and both memory and time. I could technically just do it once and then share it across problems if we had that option.
Oh, I think that's something what we could do with that sort of global problem.
Yeah.
So we could have a global problem has sub-problems.
And then that could have like a shared sensitivity.
Right. So that's something what we could do. Or I don't know, like you could probably pair the problems, but I'm not sure how.
I think pairing problems is sketchy because it's unclear like what you should be sharing between them.
Right.
But I think the global problem would be a good approach, and then specifically say that we want to share sensitivities. Do you have an example?
I can make it happen. Yeah.
Okay. Yeah. If you have an example of it, then we can sort of start sketching something out from there.
Yeah, sounds good. I'll publish the joint problem and it will be in there.
Okay. Cool.
Nice. Happy to know it's possible.
Yeah, I think that that's